This video is in continuation with the first part, which is interference of light, part 1. So look at that and then watch this video, because then that will make it easier for you to understand. We are talking of Young's double slit experiment here. Continuing with our discussion, we'll first talk about what is constructive and what is destructive interference. As waves travel from two slits S1 and S2, I'll just quickly draw the diagram once again over here. We had a source S over here, and then we have a screen, and in the screen there are two slits S1 and S2, and waves from this overlap and they reach a screen S, which is placed over here. Now as waves travel from S1 and S2, they interfere, because we know that you get a diffraction over here, and again waves diffract at the other slit, and then since they are overlapping, they will combine and form a interference pattern on the screen S. Now at points where the light waves from the two slits interfere constructively, the screen is brightly lit. So in case of constructive interference of the waves, you get a bright fringe. So the screen is brightly lit at a point where the waves interfere constructively, and at points where the interference is destructive, which means that the waves are cancelling out each other, at that point the screen is dark. Now why is this so? In case of constructive interference, which is the first case which is shown over here, the resultant vibration has an amplitude which is double that of either of the waves. Suppose the amplitude of this wave is A and this is also A, then the amplitude of the resultant is going to be 2A. Whereas in case of destructive interference, if the amplitude of this wave is A and this also is A, but the amplitude of the resultant wave is 0. If you notice, when the waves are meeting in this case, they are in phase with each other, and at each point, if we add up the effect of the two waves, we get a wave which looks like this. Whereas in this case, you have one wave and then you have the other wave which meets it, but it is out of phase. There is a phase difference of 180 degrees or pi. So in this case, if you add up the amplitudes at every point, then you can see that they will add up and give you a resultant amplitude of 0. So in this case, the waves are out of phase. There is a phase difference of 180 degrees or pi, and this is a case of destructive interference, whereas the former was a case of constructive interference. Whereas this is constructive interference, since the amplitude is double, the intensity that you will see will be 4 times of this, since I is proportional to the square of the amplitude. So this is constructive interference. We'll take a look at Young's double slit experimental setup. Waves reaching point P on the screen are traveling different path lengths, say S1P and S2P. Now this difference in path length, say S2P is greater than S1P, so S2P minus S1P is the difference in path length for the waves which are reaching point P. Now this difference in path length introduces a phase difference between the waves. So the waves which reach the screen might be in phase or out of phase. If the path length difference for waves reaching a point on the screen is an integer number of times the wavelength, then the waves meet in phase and they produce constructive interference. See, this means that if the path length difference, which is S2P minus S1P, and which we are writing as delta L. Now, if delta L is equal to m times lambda, where m is an integer, say 0, you have positive and negative values for points below and above the axis. So points above would have positive integer values and below would be negative integer values for the fringes. Now if the path length difference is delta L, which means we have, say, waves traveling from a point over here, and similarly you have waves traveling over here, and when they leave at S1 and S2, the two waves are in phase. Say this is S1 and this is S2, and this is a point P on the screen. Now the waves are traveling different distances. S2P is traveling a greater distance than S1P, and say this difference in path length over here, this difference in path length, say this difference in path length is delta L. This difference in path length is delta L, and if it is an integer number of wavelengths, that means one wavelength, 2, 3, 4, 5 and so on, then the waves at P will meet in phase with each other, and hence you will get constructive interference, which means that you will observe a bright fringe. This would result in constructive interference and hence a bright fringe. So bright fringes are formed at positions where the path length difference is an integer number of times the wavelength. Now let's look at this case. If the path length difference is half a wavelength more than an integer number of wavelengths, then the waves arrive out of phase with each other. The waves are out of phase and they cancel each other out, and you get destructive interference. So this is a case of destructive interference, and this means zero intensity, no brightness and a dark fringe. Now this happens when S2P minus S1P, which we've called as delta L, is m lambda plus half a wavelength more, or we could put this as m plus half times lambda, where m is once again 0 and positive as well as negative integer values. See, in this case, if you look at the path length difference, now we have a point P on the screen at which we are considering the waves. Waves that leave S1 and S2 are in phase with each other, but since they are traveling different distances, a phase difference has been introduced between them, and this path length difference delta L over here is a full wave that is still here and half a wave more. That means it is a full wave plus half a wave more. Hence the two waves are meeting out of phase at a point P on the screen, where you get destructive interference or a dark fringe. Now in Young's double slit experiment, we are going to derive the fringe positions. So for this, we'll take a look at the path length difference. See, the path length difference is going to be this distance over here. This is delta L, the path length difference. Now say we have this point on the screen where the angle made with the center is theta. So this angle over here is theta. Now if this is theta, this angle over here is also going to be theta. See, this angle over here is also going to be theta. That is because this line S1 S2 is perpendicular to this line, and the other line which we have dropped over here, this perpendicular, and let me call this say C, this line S1C is perpendicular to the line S2P. So the angle between these two lines is also going to be theta. The path length difference delta L equals m lambda gives us a case of constructive interference, and now delta L, which is equal to d sine theta, is equal to m lambda. See, if you look at this little triangle over here, then sine theta is equal to the opposite by the hypotenuse, so which is S2C over S1 S2. S2C is delta L and S1 S2 is the distance between the two slits, which is d. So we have d sine theta equals delta L, and this equals m lambda gives us a case of constructive interference, whereas delta L equals, and if the path length difference is m plus half lambda, we get the position of the dark fringe. If you note theta over here, what is theta? Theta is the angle the light path or the direction of the incident light makes with the central axis, makes with the central axis, and d, which we have used, is the separation between the slits, the separation between the slits S1 and S2, and lambda is the wavelength of the incident light. This is the wavelength of the incident light. Of the incident light. Now we can write the corresponding angular position of the bright fringes. So the angular position of the bright fringes can be written as theta is equal to sine inverse m lambda over d, and the angular position of the dark fringes would be theta equals sine inverse m plus half lambda over d, and in cases where theta is very small, this could be approximated with m lambda over d, and the other could be approximated with m plus half lambda over d, because for very small angles then sine theta is approximately equal to theta. Now the angular separation of the fringes can now be written as, that means the distance between two bright fringes or two dark fringes would be delta theta equals lambda over d, because you would have one bright fringe at 1 lambda over d. See, one bright fringe would be at 1 lambda over d. The next bright fringe would be at 2 lambda over d, which means the separation between two fringes is lambda over d. Same is the case with the dark fringes. One dark fringe would be at 1.5 lambda over d. The next dark fringe would be at 2.5 lambda over d. So the distance between two dark fringes would also be lambda over d. So this is the angular separation between the fringes. Now if you want the linear separation, which means the distance between the fringes, see, that would be just a minute. Now the separation between the fringes in terms of the distance would be the separation between the fringes x would be d times, because d is the distance between the screen and the slits and the screen, would be d times lambda over d, where once again let's look at the different symbols that we have used over here. D is the distance of the screen from the slits, lambda is the wavelength, and small d is the separation between the slits. You get this relation between the angular separation. Say this is theta, this is the length of the arc, and this is the radius r. Now you have theta is equal to L over r, which means L is r theta. Over here in this case we have the angular separation as lambda over d, and the distance is capital D, so we put this over here, d lambda over d, and denoting L by x, we get the separation between the fringes as d lambda over d.